Hello differential equation students. In this video we're going to take a look at how do we solve differential equations using Laplace transforms, and especially we're going to take a look at more Laplace transform formulas, and especially this first translation theorem. If you recollect, previously we looked at how to solve an initial value problem using Laplace transforms. Now today we're going to take a look at solving more of these differential equations, something of this type, and how do we do them in a much more easier way. So let's take a look at this formula right here, this first translation theorem that says, suppose if Laplace of small f of t is equal to cap f of s, and a is a real number, and suppose a is a real number, then Laplace of e to the at, that a is a real number, f of t is equal to f of s minus a. What do I mean by that? So if you want to understand this better, if you take a look at this one, so this is what this one says. Suppose if you have a function f of t and you're finding the Laplace of that, and that gives you f of s, and now you want to find the Laplace of the function f of t multiplied by e to the at, then what happens is, then if you're multiplying e to the at, all you're going to do is you're going to replace this s by s minus a. So you're going to do this first, right? This first you're going to find the f of s, and then what do? Replace the s by s minus a, s to s minus a. So you're going to have f of s minus a. I'll show you in a minute in an example what do I mean by that. All right, so let's take a look at this particular one right here. So for example, I have to find the Laplace of e to the 2t t cubed. I don't have to worry about the e to the 2t for now. Again, by the way, trying to find this Laplace using the formula is going to be a very long, it's a long way of integration, right? So how do we do this in an easier way? So first we're going to find the Laplace of t cubed. And then what we are going to do, then we are going to replace s by s minus 2 because of that 2 right there. So first what I'm going to do, let me find the Laplace of t cubed. You all know that would be 3 factorial over s to the 4, right? That will be 3 factorial over s to the 4. And so therefore Laplace of e to the 2t t cubed would be 3 factorial over s to the 4, but rather than s to the 4, now we are going to have we are going to replace the s to the 4 by s minus 2 to the 4, and that's it. And that is this first translation theorem right here. Let's take a look at this one. How do we do this? So if you take a look at this one, e to the 3t, Laplace of e to the 3t sine 2t, first what we're going to do, we're going to find the Laplace of sine t, right? The Laplace of sine t, as you know, is sine 2t, right? As you know, this is, since it's a sine, it's going to be a constant on the top, so it's going to be 2 on the top divided by s squared plus 2 squared, which is 4. Now what we are going to do, since e to the 3t is multiplied, we are going to replace this s squared by s minus 3 squared. So therefore the answer for this would be 2 over s minus 3 the whole squared plus 4, right? That's all it is. So basically what you are going to do, and or what you're doing, is replacing s by s minus a, and that's what this means right here. That's what that means right there, right? And that's how we would do these problems. All right, now let's use this idea, let's use this formula to find the solution to this particular differential equation. So let's see how do we do that. So if you take a look at this, right, we know how to solve this one. We have been doing this for we looked at an example before. First, what we are going to have, we have a differential equation, and using the Laplace transform, we are going to transform this into an algebraic equation, right? This differential equation is y in terms of t, and then the algebraic equation is going to be, cap y in terms of small s, and then you're going to solve this algebraic equation. You're going to solve for the cap y of s, and then you're going to use a Laplace inverse transform. And when we use the Laplace inverse transform, then we are going to have the solution y of t, and that is the solution to this differential equation y of t, right? That is the usual process that we have been doing all along, from here to here to here to here, and that's what we're going to repeat this here as well. So let's do that. The step number 1 is to apply the Laplace. So I'm going to say apply Laplace transforms. When I do that, my left hand side is going to be this Laplace of y double prime minus 4y prime plus 4y, and the right hand side is going to be Laplace of t squared e to the 2t. Right, we're going to use the y of 0 and y prime of 0 in a moment, right? All right, but before I go, if you try to do this in a usual way, this is the t squared e to the 2t. If you're using operator method or operator method or even superposition method, right, whatever the method that you use, this is going to be, because of this, you will see that you're going to have to find the yp, you're going to have a whole lot of constants that you have to work with, and that's not going to be pretty, right? It's going to be even more challenging. Probably you're going to have 5 constants to work with. So but when we apply the Laplace, things are going to make much simpler. This is going to make the things, solving this much simpler. So let's take a look. Again, we all know this formula already, which we looked at it before. So we're going to use these, these formulas right here, the Laplace of the derivatives, right? L of f prime of t is equal to s f of s minus f of 0. L of f double prime of t is equal to s squared f of s minus s f of 0 f prime of 0. We're going to use that in here. And it's a second order, by the way, right? So if I use that, then what happens? As you see here, then this is going to be, this would be s squared cap y minus s times y of 0, and then minus y prime of 0. This is for this particular one, right? Let me use a different color for this. This is for this particular one, right? That's coming off of this right here. The second one, if we apply the Laplace on the second one, let me use a different color, which is minus 4 times the y prime. If I use the Laplace on that one, this is going to be s times the cap y minus y of 0, right? Let me change the color here as well. And if I, for the third one, if I keep as is the same color, this is going to be plus 4 times, the Laplace of that would be cap y, right, is equal to, now that I'm done with the left hand side, if I take a look at the left hand side, if I take a look at the right hand side, let me change the color. This is going to be, we are going to, since it's because e to the 2t is multiplied by the t squared, rather than looking at this way, what we can do, that this is same as Laplace of e to the 2t t squared, right? And because of that, because of this, right, because of this translation theorem right here, right, and the e to the at, here what I have is e to the 2t. So what I can do is, this is going to be simply the Laplace of t squared, replacing s by s minus 2. So you all know the Laplace of t squared. The Laplace of t squared is, it's going to be 2 factorial over s cubed, right? That's going to be the Laplace of t squared. And so therefore this would be 2 factorial, which is 2 divided by s minus 2 cubed, right? And that's all we have. So just in case, let me just write it down here. this comes off of that, and this comes off of that, and this one comes off of that, right? Now I'm going to simplify now. Let me do that, but before I do that, let me also make sure that I'm plugging in my initial conditions now. So I have my initial conditions: y of 0 equal to 0, y prime of 0 is equal to 1. So this is going to go away. Because of that, this is going to go away, this is going to remain as 1, and here is also that's going to go away to 0, right? So if I do that, what's going to happen is this is going to be 0. No, that is going to be 0, and this is going to become 1, and that is also going to go to 0, right? So when I do that, then what's going to be what I'm left with? I'm going to be left with s squared cap y as a function of s here, by the way, minus 1 minus 4 times s times the cap y minus 0, it's not a big deal, plus 4 times cap y is equal to 2 over s minus 2 the whole cubed, right? And then what happens is, then what you see here is going to be, if I simplify, now I have an algebraic equation, right? So we are right here. So we are right here from a differential equation, applying the Laplace transform, we got this right there. We have an algebraic equation. Now our goal is to solve for the y of s. So if I do that, that's my step 2. And I'm going to pull out the cap y's. If I pull out the cap y's, then you agree I'm going to have s squared minus 4s plus 4. Good deal. And I'm going to take this 1 on the other side. I'm going to take this 1 on the other side. When I do that, this negative 1 is going to become positive 1. Or in other words, think of this adding 1 on both sides. So I'm going to have 1 plus 2 over s minus 2 cubed, right? Now if I simplify this, now if I solve for y, ladies and gentlemen, you would agree that I'm going to have y as a function of s, which I'm not writing it down, is going to be 1 over, and by the way, you all know this, you know, you're all experts in factoring, you all know this, that is s minus 2 the whole squared, which then therefore this is going to be 1 minus 1 over s minus 2 the whole squared plus 2 over s minus 2 the whole cubed, right? That's all I have, right? That is what I am going to have. Now all I have to do is to simply solve this. To solve this, now we are right here, right? I'm going back to my steps. We are right here. We have a solution y in terms of x. Now the next step is to apply the Laplace inverse to get the y in terms of t. So let me do that. If I do that, then my next step, say apply Laplace inverse transform. When I do that, then I'm going to have Laplace inverse of cap y as a function of s is equal to small y of t. You know that. This is going to be Laplace inverse. Again, I'm going to use the linearity property in here. It's going to be 1 over s minus 2 the whole squared plus Laplace inverse of 2 over s minus 2 the whole cubed, right? Now how do I apply this? So it's the same thing that we did before, right? It's the same thing that we did before with the Laplace, you know, Laplace inverse transforms, right? That is the same idea here that we applied it over there, right? If L of e to the at f of t is equal to f of s minus a, then what would be the Laplace inverse? What would be the Laplace inverse of f of s minus a? And that will be e to the at f of t, correct? And that's what we are going to use right here. This is the formula that we are going to write to use that right here to find the Laplace inverse in this case. So let me write down the formula in here so you can kind of see it. That's the formula that we're going to use. right? So if I apply this formula, as you see here, I have 1 over s minus 2 squared, right? And I have 2 over s minus 2 to the, actually I made a mistake in here. It should be, if I divide, this should be, that's correct. This should be 5. And this should be 5 as well. Please make a note of that. Right. All right. So now if I apply this formula right here, if I apply this particular formula right there, so again, you know, there are so many things going on. If you're not being very careful, you're going to make mistakes in here. So if I apply that in here, so I'm going to treat this as if it's 1 over s squared. I'm going to treat this as if this is 1 over s to the 5, and then apply this translation theorem. So now let me ask you a couple of questions in here. What are the Laplace inverse of what is the Laplace inverse of 1 over s squared? The answer for that would be, you all know that this is simply t. And what would be the Laplace inverse of, you know, here I have 5. What would be the Laplace inverse of 2 over s to the 5? There is no direct Laplace inverse, but we know that Laplace inverse of 4 factorial over s to the 5 would be t to the 4, right? T to the 4, but I don't have a 4 factorial. All I have is 2. How much is 4 factorial? 4 factorial is 4 times 3 times 2 times 1, which is 24. So I need a 24 over here. So to do the 24, what I'm going to multiply by 12 and divide it by 12. When I do that, then this is going to become 1 over 12 times t to the 4, right? Those are those two. Now if I apply this formula right here, right? So first translation inverse Laplace transform, then this is going to become, without s minus 2, without the s minus 2, 1 over s squared would be t, right? Because of the s minus 2, I'm going to have e to the at, so I'm going to have e to the 2t. So this is going to become e to the 2t multiplied by t. Again, without the s minus 5, this would be, without the s minus 2, this would be 2 over s to the 5 would be 1 over 12 t to the 4. Because of the s minus 2 in here, now I'm going to multiply e to the 2t 1 over 12 times t to the 4. I'm just rewriting it, certain things down here and there, but you get the idea. And that is the solution y of t for the given differential equation. As you see here, this process also, you know, it's a highly critical thinking, intense problem. We're using a lot of formulas in here, but this process is much simpler than, you know, the process that we're used to in our previous section. So this is a much easier way to solve this. So here is the one way that we can solve differential equations using Laplace transforms. I will stop it right here. In the next video, we'll take a look at, you know, a few more formulas and how do we solve a few more differential equations using the Laplace transforms.